Hey everyone, I am Neemias Martins.
And I am Pedro Mattos, and today we will present our work on folding entropy of the zip-shift map. This presentation is divided in three parts. First, we will present zip shifts, their definition, and some properties. After, we will present the definition of the folding entropy. And finally, in the last section, we will present our results. We first present the zip-shift spaces. Let's consider two sets, Z and S, with finite many elements. The cardinality of S is bigger than that of Z. We also consider a function kappa that is surjective. We will consider the following sequences. The entries with negative indices belong to Z, and those with positive indices or 0 belong to S. The space of all such sequences is denoted sigma. To define the measurable structure of the zip-shift space, we first define cylinders. So this is a basic cylinder set. And the general cylinder set is an intersection of basic cylinders. We denote the sigma algebra generated by all the cylinder sets as C.
We can endowed this measurable space with a probability measure. For that, let this family Pz be a probability distribution associated to the symbols of Z, and define for every element of Z and I less than 0, the measure of this basic cylinder set being Pz. Now, for any symbol of Z, we consider this probability distribution associated with S in the pre-image of Z by kappa, and define by Ps the measure of this basic cylinder by this product. The measure of a cylinder set defines the product of its basic cylinder sets. In this way, we can create a measure μ and obtain a probability space. We define now the zip-shift map, which is an extension of the usual shift map. The behavior is very similar. Let sigma and kappa be as stated previously. Denote M and L be the cardinality of Z and S. The map shifts the sequence to the left side and maps the x0 to kappa x0. And the map is called zip-shift map with ML symbols, or simply the ML zip-shift map. This map is also invariant under the measure μ. And the zip-shift map is rich in topological and ergodic properties, which allow us to study others map under conjugation. We now define the ML Bernoulli transformations. A locally invertible measure preserving transformation F defined on a bag space is an ML Bernoulli transformation if it is isomorphic in the measure context to ML zip-shift map.
So let's consider now the following example. We take M to be the square with sides 1. We define the map F as this formula here. Basically, what F does to our square is the following. In the first step here, we will stretch in the x direction 4 times, and we will shrink in the y direction by half. Next, in the second step, we take the second half of our stretch rectangle and glue above the first part. We obtain this smaller stretch rectangle. And finally, the white rectangle is put over the black rectangle to obtain our final square. To define a conjugation with the zip shift, we first number each of these vertical bands by numbers 0, 1, 2, and 3, respectively. And the horizontal bands we define as A and B. Now we can consider the zip shift with the set Z as being A and B, and the set S as being 0, 1, 2, and 3. Our map kappa maps 0 and 2 to A and 1 and 3 to B. What this encodes is that the vertical band 0 and the vertical band 2 are mapped to the horizontal band A, and the same respectively for 1 and 3. In the same way we have defined the 2 to 1 Baker's map, we can define the n to 1 Baker's map. The formula is analogous. This transformation is a 2 to n Bernoulli transformation.
Now we will take a look at the folding entropy. We need to define first what is the quotient measure and what is a disintegration of a measure. For the quotient measure, let M be a probability space, let P be a measurable partition of M, and let pi be the canonical projection that takes X and sends to P of X, which is the element of the partition P that contains X. We define the sigma algebra of P by B hat, and the quotient measure μ hat is defined by the push forward of the measure mi by the canonical projection.
In this picture, we can see our space M represented by the rectangle. Each horizontal line in this rectangle is a part of the partition. So, for instance, this red line is going to be one part in the partition. Any point x on this red line is going to be projected by pi to the element they belong to in the partition. So pi x is the element of the partition, is this red line itself. When we have a subset Q of the partition space P, this set is defined to be measurable if this pre-image is measurable in the original space M. Our original measure is defined in the space M, and the new measure is defined in the space P of the partitions. Let us now explain what is the disintegration of a measure. The disintegration of mu with respect to the partition P is just a family of probability measures, this family mu P. Each probability measure is defined on M, but the first property is that mu P gives total measure to the set P. So the measure mu P lives on the set P. Second, for every measurable set E, if we consider the map that takes each P to the measure mu P of the set E, this map is measurable. And finally, and the most important property, for every measurable set E, we can calculate its measure by disintegrating it. That is, we have an integral over all the parts of the partition, and we measure this set in each of these parts, and the integral is relative to the quotient measure. If we go back to the picture, we can think each measure mu P lives inside here. So to calculate the measure of any set E, calculate the measure in each of these leaves. And then we integrate over these leaves here with respect to the measure mu hat.
In order to define the folding entropy, let epsilon be the partition of M into single points, and consider the pre-image partition of F. The folding entropy was first introduced by Ruel and is defined by the conditional entropy of epsilon relative to the pre-image partition. Now we see some properties of the folding entropy. First, if there are n pre-image branches, the folding entropy will be bounded by log n, and the equality will be achieved if all n pre-image branches are equally mu weighted, and will be 0 if we have a diffeomorphism, since n will be 1. As example, we have an image where this transformation F maps n elements to 1. Then the folding entropy of F will be bounded by log n.
We now present our results. The first theorem is this one. We're in the context of the zip shift map. In this case, the folding entropy is given by this sum. Here is the Shannon entropy of this distribution, and here is an element of the P distribution. Let's consider again the example of the 2-to-1 Baker's map. We have the sets Z and S as before, and also kappa. The distributions we consider are the uniform distributions, given by half on each entry. Then by our formula, we have that the folding entropy is the sum, which if we expand and evaluate at each uniform distribution, we obtain this. Each one of these is log 2. So we obtain the final result of log 2. In general, for the Baker map n-to-1, we have the floating entropy is log n.
We want to give you an idea of the proof. Denote an element of the pre-image partition by x hat, which is the set of these points. And for a measurable subset Q, denote Q hat by the set of all x hat where x belongs to Q. So Q hat is a subset of the pre-image partition and satisfies this equality with the canonical projection. And the quotient measure of the Q hat is given by the mu Q. So, from a basic cylinder set Cij, the quotient measure of the Cij hat is just Pj. Now, for every x hat of the pre-image partition, the disintegration measure in x hat will be the Q x minus 1 s, where Q x minus 1 is the probability distribution associated to x minus 1. And the family of probability measures will be a disintegration of mu with respect to the pre-image partition.
Now we denote by epsilon sub x hat, this set. This is basically the partition of x hat induced by our epsilon partition. So we partition x hat in atoms. So by the definition of mu x hat, this entropy will be equal to the Shannon entropy of this distribution Q x minus 1. And finally, this is the last calculation. This step is by the definition of the conditional entropy. We have here the entropy we have calculated before. This step is because sigma minus 1 epsilon is the union of these cylinders. And finally, we just substitute the values and we obtain our final result. And this is our last result. It relates the Kolmogorov-Sinai entropy, or topological entropy of our system, to the folding entropy. First, this is the topological entropy. It can be calculated as the entropy of the partition by cylinders, but it also can be calculated as the sum of the folding entropy and the entropy of the distribution P. And finally, we can just change the entropy of the distribution P by the entropy of the C minus 1 partition. In particular, if we have the usual case of Z equals S and kappa is the identity, so our sigma kappa is just the standard sigma Bernoulli shift. And so we have these equalities, and the folding entropy is 0. And these are the references we have consulted. Thank you.
Thank you.